Grade 9 Current Electricity. Part 1. The Concepts and Circuits. So what's happening in a circuit? Two requirements are necessary for current to flow in a circuit. A source of energy, here we have two cells in series, and this battery has a voltage of 18 volts. And the other is to have a closed circuit. So I've closed the switch, and now you can see the little electrons are moving around. So the cell is the giver of energy, and the light bulb and the resistor, whatever appliance this represents, is the user of energy. We see that even when the switch is open, that the cell or the battery can give 18 joules of energy per charge. But when I move this here, then we see there is no current, and therefore no energy is used up because nothing's moving. So that voltage is 0, but once I close the switch, we see there's the 18. But the 18 has to be shared between the appliance, this resistor, and the light bulb. So if I look at the voltage across just the bulb, we see it's 12 volts, and the rest of the energy is used to get through the resistor or the appliance, whatever it represents. But we see this is 6 volts, and the two together add to 18 volts. The Phet Simulation. When I close the switch, you can see there's a 9-volt battery powering the light bulb. You can see how bright it is. The current is 0.9 amps. When I have two cells in series, we can see the light bulb's brighter, the voltage is bigger, and the current is bigger also. When I have three in series, then the voltage is much bigger. It's 3 times what it was on the left, and the current is 3 times more. We can see the little electrons are moving really fast, and the bulb is very bright. Now, we want to contrast that with connecting things in parallel. If I have 3 cells in parallel, the bulb doesn't get brighter, the current doesn't get more, it stays the same, and the voltage stays the same. So what's the advantage? Well, you can see the charge is moving really slowly through the cells because they're only giving energy to every third charge. So what's happening in a circuit? Well, the cell is the giver of energy, and the resistors are the users of energy. They convert it to some other form of energy. The 4 concepts, that of charge, current, potential difference, and resistance. Electric current, it's the flow of charges in the circuit, and in metal conductors, it's the electrons that move. There are 2 requirements. There must be a source of energy, like a battery, and the current can only flow when the circuit is complete. There's a continuous pathway. It's a closed circuit. Current strength is how quickly the charges are moving. The charges per second. Definition, the rate of flow of charge. It's measured in amps by an ammeter that's connected in series, and in metal conductors, it's electrons that flow. Before we even knew about electrons and subatomic particles, we knew about electricity, and conventional current was defined as the positive flow of positive charge. So that is still used across the board. The analogy of current is water flowing in a pipe. Potential difference. Definition is the energy transferred per charge between 2 points in the circuit. The symbol is a V, both for voltage and the unit of a volt. Through a cell, the charges gain energy. So the energy is transferred to the charges, and through an appliance, it transfers the energy to something else, like heat or light or motion or sound, or even cause chemical reactions in electrolysis. It's measured by a voltmeter, which is connected in parallel, because it's trying to measure the difference in potential between 2 points in a circuit. The formula is energy per charge. We use a W instead of E for energy because work and energy are synonymous, so we need the E for something else. The analogy for water in a pipe is the pressure in the water pipe that causes the water to flow. So if current is water flowing, then the pressure pushing it is analogous to potential difference or voltage. And why is there pressure in the pipes? Because the dam is higher than the tap. And that's what causes the water to flow. So voltage causes current to flow. Resistance, it's resistance to current, resistance to the flow of charge. R is given by the voltage divided by the current, and it's measured in ohms. We learned earlier this year the factors affecting resistance: length, the longer it is, the greater the resistance. The thicker it is, the less resistance. Think of a thick pipe. More water can flow than a thin pipe. Resistance depends on what the substance is made of. Silver is the best conductor, but we use copper because it's cheaper. And temperature. Well, you've got to heat it quite a lot, but certainly in a light bulb, it gets hot enough that its resistance increases. Conductors have very low resistance, and insulators do not conduct. They have very, very high resistance. And resistors and semiconductors are somewhere in between those extremes. To summarize these four concepts, charge, we give a symbol Q and it's measured in coulombs, but in grade 9 we don't use that very much. Current, we use a symbol I, measured in amps, and the definition is the rate of flow of charge. So you could think of a coulomb per second as being equivalent to an ampere, and it's measured by an ammeter in series. The definition is the rate of flow of charge, which this formula shows. Potential difference or voltage, symbol V, same with the unit, and its formula. It's the energy per charge, so joules per coulomb, and measured by a voltmeter, and energy per charge, difference between 2 points in a circuit. If there's a potential difference, the current will flow. Resistance, it's resistance to current. R is the symbol, it's measured in ohms, the omega sign, and it's given its value by dividing the voltage by the current. Some symbols that we use: a cell. A battery is 2 or more cells. It could be in series or in parallel. Switch, open and closed. Bulb, voltmeter, ammeter. A resistor, which could represent any appliance. A variable resistor we call a rheostat. An example of that would be a dim switch for a light or a temperature control for a stove. Electronic components: a diode, the arrow shows the direction in which the current flows. It restricts it to flowing only in one direction. A light-emitting diode is the same symbol with a circle around it and arrows showing that it's emitting light. It's going out. LED, light-emitting diode. And they're more commonly used nowadays than incandescent bulbs, and there's a little one. LDR, the light's coming in, it's a light-dependent resistance. So as the more light comes, the value of the resistance changes. And here we see the actual component, and these can be used for light sensing circuits, controlling shutter speeds in a camera, street lights that switch on after sunset, can all be controlled by having a circuit with one of these in it. And a thermistor is a sensitive, thermally sensitive resistor. So it changes its resistance depending on the temperature. So more so than in standard resistors, and it's used as temperature sensors, especially in difficult to reach places like the temperature inside an engine of a motor car. Sources of energy, well, cells, electrochemical cells, that converts chemical potential energy into electrical energy, which can be thought of as the kinetic energy of the charges that are moving. It makes DC, which is direct current. It only flows in one direction. Solar panels are an array of PV cells, photovoltaic cells, photons that are making voltage. They also make DC, but a generator like Eskom uses makes alternating current, AC. It changes direction, alters its direction. In fact, in South Africa, 50 times per second. We say it has a frequency of 50 hertz. The generator is a bit like a motor, except spinning it makes electricity. So if a motor uses electrical energy to make kinetic energy, the generator does the opposite. The same instrument can be used for both purposes. A car, it's called an alternator. Ohm's law, part of the GEC. This was the circuit that you used. We see a single cell, and we measure the voltage and the current, and then we add a second cell and a third cell and see how the current responds. The current is dependent on the voltage. So Ohm's law states that the current through a resistor is directly proportional to the potential difference or voltage across the resistor and inversely proportional to the resistance. So the bits that are in bold are the bits that are relevant to the investigation you did. How does the voltage affect the current? Variables. We're trying to see how the current depends on the voltage. This is the one we change by adding cells, and when we plot it, it's on the x-axis, and the current is on the y-axis. And the control variables is the resistance itself and the temperature. So imagine we had taken these readings. Now they're not perfect readings. We can see the ratio is not exactly 5, but it's more or less. If we had to plot those, we end up with points that look like that. Now we need to draw a graph, a line graph. Well, it's not correct to do that. It's not as if at some special voltage the relationship is changing. So we don't do that. Instead, we draw the best straight line through all the measured points. So none of the points actually need even lie on the line, but we are looking for that. Remember that when you're taking readings, there's always a margin of error in each one, and some of the voltmeter readings were jumping around when you were doing it. So plus or minus an acceptable amount of experimental error shows that as the voltage increases, so does the current, and it does so proportionally. The current is directly proportional to the voltage. That's what we can conclude from the graph. Showing it a different way, as the voltage increases, so does the current. So if I consider a voltage of 1, and then compare the current at that time, when I double the voltage, so the current also doubles. So 10 is twice the value of 5. And if I go to 3 volts, well, then we see 15 is 3 times 5. So as the voltage increases, so the current increases proportionally. When we have a straight line, we want to know the slope. You know how to measure it. You've done this in maths. It's the rise over the run, the change in the current value, the y value, over the voltage value, the x value. And that is the inverse of resistance. So the conclusion is the current is directly proportional to the voltage. Now for circuits, the difference between series and parallel circuits. Here, there's only one pathway, and the current must go through a series of things along the route. that's where it gets its name from. Whereas in parallel, there's multiple pathways. So if charges are moving along here, they either pick up energy with the bottom cell or the top cell, and then they come around and they either go through the top resistor or the bottom resistor. And here we have it splitting three-way. The Phet simulation. When I close the switch, you can see there's a 9-volt battery powering the light bulb. You can see how bright it is. The current is 0.9 amps. When I have two cells in series, we can see the light bulb's brighter, the voltage is bigger, and the current is bigger also. When I have three in series, then the voltage is much bigger. It's 3 times what it was on the left, and the current is 3 times more. We can see the little electrons are moving really fast, and the bulb is very bright. Now, we want to contrast that with connecting things in parallel. If I have 3 cells in parallel, the bulb doesn't get brighter, the current doesn't get more, it stays the same, and the voltage stays the same. So what's the advantage? Well, you can see the charge is moving really slowly through the cells because they're only giving energy to every third charge. Charges are splitting and going, the pathway of the charges is splitting, and each cell is only giving energy to every third charge. So this battery will last 3 times longer than that one. Now, let's look at connecting resistors in series and in parallel. Again, that's what we had before. Now, I'm going to add a second bulb in series. Notice the current is a lot less. Charges are moving slower. The voltage across both is 9, but across each one is only 4.5. So the total energy is divided amongst the two. 4.5 volts across each one. Contrasting that with adding them in parallel. That's what we've got in the first one. Now, when I add the second bulb in parallel, I want you to notice what happens to the total current. Notice how it increases. So when you're adding resistors or bulbs in parallel, the total resistance gets less because you're adding another pathway, and that means the total current increases. So what we've seen is, if we add cells in series, each time the light bulb got brighter and brighter. So the voltage here is bigger than the number 2 and bigger than number 1. So as the voltage increases, the current increases, and that's why the bulbs are brighter. Now let's add the resistors. So compared to this one, we've added an extra bulb, an extra resistor. So it's slightly dimmer than the previous one, and that would be dimmer still. So as we add resistors in series, the resistance increases, therefore the current decreases, and that will make the bulb dimmer. That's the one argument, using resistance and current. But we can also talk about the voltage. If we look in the last circuit, this total voltage divides amongst these. We call it a voltage divider, and the total voltage, Vt, must be equal to the sum of the other 3. So if each is 2 volts, this is 2 volts, the charges pick up 2 and another 2, so that's 4 volts, and this would be 6 volts. Over here, we would see that these two would be the same if the bulbs are the same, and they must each be 3 volts. And here, all 3 of those must be the same, so 6 divided by 3 gives me them all equal to 2 volts. Let's contrast that with circuits in parallel. Adding cells doesn't make a difference to the brightness of the bulb. It's the same voltage, the same current, and the bulbs are equally bright, but this battery would last longer. So as the charges come through, they pick up 2 volts and carry on. Some of the charges go the other route and pick up 2 from the other. So these will last, this battery will last twice as long as that cell. Now we're going to add resistors in parallel. So we're going back to that situation, and now we're adding another resistor in parallel. And finally a third one. Now the bulbs don't get dimmer. So it's the same voltage across each of them. But the total current increases because we're adding an extra pathway. And so the current will be biggest out of all of these circuits in that section. So when you add more resistors in parallel, because you're adding extra pathways, there's less resistance. The resistance decreases. To calculate the value of the resistance is not as simple as series, where you just add them up. We have these two formula. 1 upon Rp is 1 upon the one plus 1 upon the other. This will work, and you can just keep adding more in this formula. But if you only have 2, then you can use this as an alternate. What does happen, though, is the current divides. So if ammeter A5 is measuring the current I5, and these are each measuring currents I6, 7, and 8, if you add those 3 up, it must equal to the current in that portion. That's the total current. This is how lights and plugs are connected in buildings. Another way of summarizing it without all the meters, when you add resistors in series, the resistance increases, and therefore the current gets less, and if they were bulbs, they would burn less brightly. Adding resistors or bulbs lowers the total resistance, and thus the total current increases. So the current over here increases as you add more of them, but they burn equally bright. So if we had a voltmeter across each one, we would add them up to get the total voltage. The total voltage divides amongst the components in series, and here it's the current that divides. So the total current coming along here is equal to the sum of the current through the 3 resistors, and there it joins up again. Whereas here, there's only one pathway, so the current is everywhere the same. And here, the voltage is everywhere the same. Let's practice 2 calculations. Here we have a series circuit. And the voltmeters, if you're building a circuit, always build the circuit first and then add the voltmeters afterwards. They are connected in 2 places, they're in parallel. Now, if each of the cells is 2 volts, calculate the following. Let's look at the answers. What's the total voltage across the battery? Well, the charges pick up 2 and another 2 and another 2. So the voltage is 6. The total resistance, you just add them up. So it's that one, 4 plus 3 plus 5 gives you a total of 12 ohms. And if I want to work out the ammeter reading, now I know the total voltage and I know the total resistance. So I can use my formula. I is V over R is 6 over 12 is 0.5 amps. And the current is everywhere the same. There's only one pathway. Well, what's the reading over here? If you look just between these 2 points in the circuit, what do you know? Well, you know the resistance, and we also know the current, because the current is the same as it is there. So now we use this version. Voltage is equal to the current times the resistance. The current is 0.5. The resistance there is 5 ohms. It's not the full 12 ohms. And that gives me 2.5 volts. Let's now contrast that with a parallel circuit. Consider it below. There's a 12-volt battery. So the voltage there is 12. And the ammeter A1, that's this one, measures 3 amps. Now they want to know what's the current through this part, because the 3 amps comes and divides. Some of it goes this way and some of it goes that way. We also asked to find out what this reading is, ammeter number 3, and hence the resistance of the bulb, and then the effective resistance of the combination. Well, there's no potential difference. No energy is used up moving from there to there or from there to there. And the same on the other side, and hence the voltage across both resistors is the full amount, 12 volts. Therefore, I can work out the current through this part because I know the voltage is 12 and the resistance is 6. So I is V over R, 12 over 6 gives me 2 amps. So 2 amps is flowing through here. Question B says, what's this reading? Well, if that one's 3 and 2 of it's going this, then that must be 1 amp. The 3 amps minus the 2 that goes this way leaves 1 amp to go the other way. Now I can work that out. This section, I know the current now is 1 amp, and I know that the voltage is 12 volts across the light bulb, and hence I can use it to calculate its resistance. R is V over I. It's 12 over the 1 amp, which is 12 ohms. Last question, what's the effective resistance of the two together? Next page. Calculate the effective resistance of the parallel bit. So we often say RP rather than R total. We have since worked this out to be 12. So we're going to use this formula. 1 upon the effective resistance is 1 upon the 1 plus 1 upon the other. They're just 2 of them. We don't need that part of it. So we put them, it's 1 upon 6 plus 1 upon 12. Now how do you add fractions? You must first put them over the same denominator. 2 twelfths is a sixth, plus 1 twelfth gives 3 twelfths, which is a quarter. But that's not the resistance, that's the inverse of the resistance. So you have to flip them both over, both sides of the equation, and therefore the RP is 4. Some people prefer, and it only works if you have 2, as in this case, you have the product of the 2 resistors over the sum. And 6 times 12 is 72, and 6 plus 12 is 18, and when you divide that, it also gives you 4 ohms. And that's it so far.